So this lab is all about friction. So we talked about kinetic and static friction in class. Kinetic being moving and static when you're sitting still. So part A, you're just going to measure the coefficient of kinetic friction. So you need to hit the block to get it going. We'll talk about this in a little bit. Part B, you're going to measure not only kinetic friction coefficient, but also static friction. And in this, you're going to tilt your ramp up at an angle. So part A is flat, part B is tilted. And then in part C, you're going to look at the mechanical advantage. In other words, why you'd rather walk up a ramp than stairs. So if you remember, friction is just a force that opposes motion. And there were two types. We had kinetic, mu sub k. This is when it's moving. That's why it's kinetic. And then we also had static. This is to get it to start moving. And you're going to be finding both of these. So in the first method, this is part A. And what you're going to do, you have a mass hanger right here. If we draw a force diagram, you've got its mass, tension pulls it up. And then if we draw a force diagram of this, you will see that you have tension, its weight, and again, make sure that you add this extra mass on top of the block, because otherwise it's just going to fall off, and that's not fun. Okay, it's fun, but it's not really necessary. And by necessary, I mean you can't measure it. It's balanced by this normal force, and since it's going to go to the right, you have friction, which is mu n on the other side. So if you balance this out, you can find a way to solve for this coefficient of friction based on this mass. So when you're working on this, you're finding mu sub k, coefficient of kinetic friction. And what this means is you are going to have to give this a little tap to get going. So if we start with the little block sitting there, you give it a tap, and it will move at a constant velocity. And you'll notice right in this region it slowed down a little bit. Over here it was going a little quicker. But you want an average velocity to be constant, okay? And if your velocity is constant, this means your acceleration equals 0. And you want this to move at a moderate pace. If it goes too slow, the coefficient of friction increases a little bit, and you don't want that to happen. There's a nice discussion of this in your book. So make sure you run this at a moderate pace. So in part B, you're looking for the coefficient of kinetic friction. So you will elevate the ramp, and then if you give it a little tap, it will start moving. And you want it to go down this ramp on the average at a constant velocity, so that your acceleration is equal to 0 on the average. You will have to adjust this ramp so that this is so. If it's accelerating, too steep. If it's not accelerating, too low. So from looking at this and reading your lab handout and working through the calculations yourself, you know that your coefficient of friction somehow depends on this angle. More importantly, depends on trig functions and how trig functions relate to this angle. Now in this part, you don't necessarily need the angle. You just need to know the trig function, and to get the trig function, just use the sides of the triangle. So let's pretend that for some reason I'm interested in tangent. You just need to measure the adjacent side and the opposite side, and then you know that tangent theta equals opposite over adjacent. You have no reason to measure an angle. You don't need a protractor because your measurements with the meter stick, i.e. such as this one right here, are going to be more accurate. And it's also going to give you a great way to get your plus or minus values. So the second part of part B is to find the coefficient of static friction. So you are going to lift this ramp, because static friction is bigger than kinetic friction, so your angle is going to be bigger, or the coefficient of static friction is bigger. So you're going to lift this ramp, and it's going to keep on going. Wait for it, move very slowly, wait for it. And there it goes, just like magic. So your partner will move this little latch up, lock the lamp, and again, by lamp I mean ramp, and you will measure the sides of this triangle. Now let's talk about mechanical advantage. So, as previously mentioned, if you see this is a ramp at some angle theta. Or you see a giant wall, that is too tall of a wall. But let's pretend that this wall is both 50 meters tall. You have two people. Person A walks up here. Person B throws a grappling hook, climbs up here like a ninja. Person B may in fact be a ninja. Who knows? Let your imagination go wild. Who did more work? The answer is no one. So it's the same work. Same amount of work. So the reason it's the same amount of work, let me fix that K here quick, is because if you're looking at the work against gravity, which is mg, h, remember, looks a lot like potential energy. That's because this is your force, work against gravity. Negative mgh force times your distance it moves, delta x, make this x component. And in both cases, they went the same height, and they had the same mass, so same force against gravity. So when we talk about mechanical advantage, we are talking about a force advantage. So let's take a look. If you know that work equals Fx delta x, and we look at the distance for person 1, this would be delta x1, and this would be force of 1. You know that force of 1, delta x1, equals, and we'll make this right here, this would be delta x2, and this would be force 2, equals F2 delta x2. So because this distance right here is bigger than this distance, that means this is larger, this is smaller, which means to compensate, the force you exert is smaller, and the force over here is bigger. So when we talk about mechanical advantage, you're looking for a force advantage. Don't get something for nothing. It's just an advantage in the amount of force you have to apply, because you have to apply the force over a longer distance. So to calculate this, you're going to put this cart on the ramp right here, and you're going to roll it up and down. So you're going to have one trial where it goes up, one trial where it goes down. So by over here, you're not going anywhere. You will see, zoomed in, oh, there's the science. It goes up, and it comes down. And if we look at this on the way up, so let's go to a new slide. So if we look at this on the way up, friction's directed down the ramp. When it's moving down the ramp, friction is directed up the ramp. That's because friction's persnickety. So if you look at the tension up and the tension down, those are the tensions to keep it moving at a constant velocity. So again, acceleration equals 0. Constant velocity, you're going to have to do this multiple runs. But if you average the tension up and the tension down, not only do you have a great way to get error bars, but this is a good way to average out friction. And this is explained in the lab handout, which you're looking at as you watch the video, right? So if we're taking another look at mechanical advantage, it's just the force to pick that cart straight up, which is the weight of the cart with the extra mass, the weight of the cart, over the force to push it up, which is the weight, in this case, of the hanging mass. So it just tells you how much easier is it, how much less force do you have to apply to push it up the ramp. So if To recap a couple important procedural notes, cart's going to move at a moderate, constant velocity. All right, again, this makes sure that your acceleration is equal to 0. And also, measure the sides of the triangles to find your angles. You just need the adjacent side and the opposite side to find theta. And here's a quick recap just on a couple of things that are going to be important. You need comparisons of the coefficient of friction. You're going to find them two ways, so compare from part A and part B. I need error bounds on your coefficient of friction. And then I also need comparisons of your mechanical advantage. Just state what has a higher mechanical advantage, shallow ramp, steep ramp, and give me some data to back this up. Also, don't forget to report your mechanical advantages with error bounds. And one final note. Make sure that you answer all questions on the lab. They're in the analysis part, so make sure you answer all of them. And that's the lab.